Of course, we need to make different calculation in our course, because I already said we're in a technical university and we put all theory on exact vehicles. And talking about thermodynamics, about chemical thermodynamics, here we use special part, thermochemistry. And this is a part of thermodynamics which studies thermal effect, heat effect of chemical reactions, and their dependence on given conditions. In thermochemistry, we have special equation, not we used to use in chemistry in school. Thermochemical equations are equations which show us not just which substances react, but as well show us a heat effect, enthalpy of this reaction for smaller amounts, and of course show us which conditions we have and in which aggregational state we use these substances. We have two forms of thermochemical equations you can see in this slide. As I said, in thermochemical equation we write thermal effect, heat effect of this reaction, and we can write it through comma. So you see graphite burned in pure oxygen give us carbon dioxide. Then we write comma and we write thermal effect, delta H equal minus 396 kilojoules per 1 mole. Of course, we need to make different calculation in our course, because I already said we're in a technical university and we put all theory on exact reaction. Now we write graphite plus oxygen give us monoxide, but now plus 396 kilojoules. Let's determine we have exothermic or endothermic reaction. As I already said, endothermic reaction occurs with absorption of energy, exothermic release of energy. You see that delta H equal minus 396 kilojoules, so we can say that we have exothermic reaction. But sometimes students have mistakes, then they write thermochemical equation in a second way, because they see CO2 plus 396 kilojoules, and sometimes they can say me, okay, this reaction endothermic reaction. I agree, but not at all. We can have two ways of reaction, from left side to right, forward reaction and backward reaction. And if we mathematically replace this number plus 396 kilojoules from right side to left side of reaction, so you can see that initial reactants, they lose energy, because we commonly read reaction from left side to right side, so we can see that forward reaction, exothermic reaction, and backward reaction, endothermic reaction. For a thermochemical equation, we use several features. First, I said that thermal effect depends on the mass of reactants, of all components in our process, and we usually calculate thermal effect just for 1 mole of substance. That's why in thermochemical equation we can use fractional odds. Of course, in school, sometimes in school we used to write whole numbers, and sometimes we think if we write fractional odds, we have mistake in this case. Yes, that's true, but we don't deal with thermochemical equation, thermochemical calculations. So you can see here example, formation of hydrochloric acid from pure hydrogen and fluorine. And if we want to write heat of thermochemical equation that shows which we produce just 1 mole of this acid, we need to write fractional odds, so we have just half of mole for hydrogen and half of mole for chloride. And in this situation, according to thermodynamic table data, heat effect, standard heat of formation for this reaction minus 92 kilojoules per 1 mole. But if we rewrite such equations, such reaction in common form, so if we take 1 mole for both gases, hydrogen and chlorine, so of course it produces 2 moles of hydrochloric acid, and in this situation we need doubled our heat effect. So now we write heat effect equal minus 184 kilojoules, and as well we can say that we have exothermic reaction here. Second position, thermal effect, heat effect depend on aggregational state of all reactants in our reaction, and we need to indicate it through index for all substances. For example, we produce water. Of course, we produce it from hydrogen and oxygen, but we can make, as a result of this reaction, we can get liquid form of water and gaseous form water vapor. And if we take thermodynamic data for first reaction, when we produce liquid water, standard heat of formation minus 285.5 kilojoules. For second reaction, then combustion reaction of hydrogen gives us water vapor. Standard heat of formation minus 241.8 kilojoules per 1 mole. Seems like it's not so great difference. Okay, I agree, but for 1 mole of substance, let's imagine we want to launch in space a small satellite or roster by Elon Musk, and in this situation, obviously, they don't use just 1 mole of fuel in a rocket engine. Of course, we use tons of fuel. And for 1 mole difference in heat effect, not so important. But for tons of fuel, when we have thousands of moles, of course, difference in heat effect, very important. So, please note that in calculations to determine heat effect, we need to see in which exactly aggregational state we have reactants and products. In third position, we can make different algebraic operations with these equations. We can sum reactions, we can multiply or divide or different coefficients. So the same like we do in mathematics, we can make here in thermochemical equations. So thermochemical equations better show us than usual equations what exactly we have in this process. It shows not just qualitative and quantitative compositions of all components, but also shows quantitative transformation of energy, shows thermal effect of this reaction. And now let's discuss the main law of chemical thermodynamics. Now let's know how we can calculate exact thermal effect for exact chemical reactions. For this aim, we use the Hess law. About what tells us this law? The thermal effect of all chemical reactions, which we make in isobaric isothermal or isochoric isothermal conditions, so I mean volume and temperature are constant or pressure and temperature are constant. And this thermal effect doesn't depend on the way of reaction, but depends on initial and final state of the system. So it doesn't depend on number of intermediate steps, and doesn't depend on mechanism of all process and rate of this process. So as you see in the picture, like example, We have 2 points, and we need to reach the highest one. To reach this goal, reach with aim, we can use 2 different ways. Straight way from the left side of this picture, and from the right side of the picture you see this curved path. And for us, it's not necessary which way we use. For thermal effect, it's not necessary how many steps we make for in this reaction. We just need to reach this attitude. We just need to know initial point and final point. As well, we can explain Hess law using triangle of Hess. For example, we have combustion reaction of carbon, and as we already know, we can produce 2 different oxides. If we have excess of oxide, we can make CO carbon monoxide and CO2 carbon dioxide. All these steps had their own thermal effect. So if we burn carbon till carbon dioxide, a heat effect delta H1, or if we have intermediate step when firstly we produce carbon monoxide CO and then burn it to carbon dioxide, so we have delta H2 and delta H3 respectively. So how we can use Hess law here? Actually, the direct determination of second heat effect in experiments is very difficult, because once carbon monoxide forms, it reacts further to carbon dioxide. And experiment, unfortunately, we can separate carbon dioxide to calculate delta H2. But we know heat effect for first step and third step. As I said, we can make algebraic operations with thermochemical equations. So you can see here in this slide, in this picture, you can see 3 thermochemical equations with heat effect. And here, from these equations, if we sum second and third equation, it gives us first one. And in this situation, heat effect of second step, delta H2, it's a difference between heat effect of first step, delta H1, first reaction, and delta H3. In this situation, difference equal minus 110.5 kilojoules. So we as well have exothermic reaction. And now we can see that we easily calculated heat effect of second step, delta H2. Well, but in practice, we use not exactly Hess law, but we use consequences from this law. We can separate all reactions for production, formation reaction, and combustion reaction. Of course, for different reactions, we use different consequences. And first consequence we use for formation reaction, we can calculate heat effect as a difference between 2 sums. First sum, standard enthalpies, standard heat of formation for products, and standard heat of formation for reactants. So you see here formula, and in this formula we use not just difference between 2 sums, but we need to take into account stoichiometric coefficients in our reaction. Because they said the standard heat of formation is a heat that we need to produce just 1 mole of reactant. And we already know that in the real reaction, in real life, we also have reaction between more moles, and of course we need to put it in our calculations. So here you see that we have n of products and n of reactant numbers amount of products and reactants respectively, and we use standard heat of formation for products and reactants. Let's remind you that standard heat of formation are thermodynamic data. But we know that mostly we have combustion reaction occurs in our life, in our world. We have a lot of different organic substances, much more than non-organic substances. We need to know how to calculate heat effect for combustion reaction. Almost the same situation, but in previous consequence, firstly we write sum for products, but then we use reactants. Here we write firstly sum of products between numbers of mole for reactants and standard heat of combustion of reactants, and just then we write sum for products. And one note, of course, here we use standard heat of combustion. You see delta C, H0 and 298. So please don't forget it that for organic substances, for standard heat of combustion, we have special table. They given in our thermodynamics data. Okay, for example, let's imagine we have reaction between A moles A and B moles B, and these substances produce C mole of substance C and D mole of substance D. If this reaction, formation reaction, so how we can calculate heat effect? You see, we take C moles of substance C and multiply it on standard heat of formation for exactly substance C, then some D standard heat of formation for substance D, and then we need to calculate difference. We take A moles and multiply it on standard heat of formation for substance A and B moles of standard heat of formation for substance B. And this will be as a heat effect for standard heat for this reaction formation. But if we have combustion reaction, let's imagine that substance A, B, and organic substances. Firstly, we need to write reactants. So A mole we multiply it on standard heat of combustion for substance A plus B moles standard heat of combustion for substance B, and minus, of course, C moles standard heat of combustion for substance C and D moles standard heat of combustion for substance D. But these calculations, these consequences, we use just in standard conditions. Let's remind you what does mean standard conditions. 1 atmosphere's pressure and temperature, we have room temperature, 25 degrees per Celsius and 298 degrees per Kelvin. But let's imagine we have combustion reaction in engine, rocket engine or aviation engine. Of course, we already know that we have tons of fuel in this situation, and oxidation of fuel in this situation gives us a great amount of heat, and this in turn heat our system, so temperature increases. And in this situation, of course, reaction goes not in room conditions, but under thousands and hundreds of kelvins. And how to calculate heat effect in real conditions? Here we need to remind such parameter like heat capacity, which you know from school. Heat capacity of a portion of substance is a quantity of heat which we need to increase temperature of the substance on 1 degree Celsius or Kelvin. And in this situation, we can calculate heat of the system like product between heat capacity and change of temperature in this case. In school, in physics, you use heat capacity for 1 kilogram of all substance, but you know that in chemistry we use molar concept. So here we use molar heat capacity, and depends on thermodynamic data, depends on conditions, isobaric or isochoric conditions. We use molar isobaric heat capacity or molar isochoric heat capacity. And let's see how we can calculate in this situation heat effect of all reaction in real conditions in temperature T. So firstly, we need to calculate heat effect in that conditions which we can calculate it. So we calculate heat effect of all chemical reaction in standard condition. You see here wrote in this formula firstly delta H 0 to 198, and then we need to sum the heat to increase or to decrease maybe temperature. So we write integral from 298 kelvins to temperature to given conditions from delta Cp over dt. Here delta Cp, it's a difference between molar isobaric heat capacity for all substances. And finally we have sum of standard heat of formation of heat effect in standard conditions for this exact reaction, and delta Cp multiplied delta T. But how in this case we can calculate delta Cp? What we need to do, because in a reaction we don't have just one component, but we have at least 2 components, 3. And delta Cp in this situation we can calculate from like we calculate heat effect of formation reaction. So we use first consequence from a Hess law. So you see, firstly we take products, all parameters for products. We multiplied molar isobaric heat capacity for product on the amount, on numbers of moles for this exact product, and then subtracted from it product between molar isobaric heat capacity for reactant and numbers of moles for this reactant. And then they place this difference in molar isobaric heat capacity to Kirchhoff equation, and now we can determine heat effect of all chemical reaction in real conditions.